Okay, so we're searching for the very best estimator given the fact that we have noise and we know the statistical qualities of noise but not the noise itself. And we've termed this problem the best linear unbiased estimator, or BLUE for short, and we found that the solution is, well, actually we didn't find it, I just stated it, and now it's up to us to prove that this is really the case. A transpose R inverse. Okay, let's try this. I'll put a question mark out there. First thing we need to check is, 1, is L not A equal to I? And sure enough, it's going to be L not A is equal to A transpose R inverse A inverse A transpose R inverse, and now times A. And that is indeed equal to the identity matrix. So far so good. The next is to show that any other matrix that satisfies that yields a larger error. So next we show that it's best by showing that for any other L, the trace of L R L transpose, and that was the quantity that we're trying to minimize. That's what we showed last time that this all devolved into, is larger than that. Okay, so to do this, we will first define any other L as L naught plus, and this is tricky, watch this, L minus L naught. Beautiful. Okay, so now we have a ironclad definition for any L naught. And now we can evaluate this. The trace of LRLT is just equal to the trace. Remember, traces add because traces are a linear operation, they're just a sum of the terms on the diagonal. So get that plus the trace of L naught R L minus L naught plus the trace of L minus L naught transpose R L naught transpose plus the trace of L minus L naught R L minus L naught transpose. Okay, so where did all that come from? I think that's not supposed to have a transpose there. There we go. That came from just multiplying this term out, the L R LT, where L is defined as that quantity there. So we get this quadratic term, and we're not going to simplify it all the way. I think we would find if we did, we would get a bunch of terms that would just cancel. So one thing to note, this term right here and this one right here are going to be the same. And so we'll come back and revisit that in a minute. So now we already have an expression for L naught that's given above. So let's go ahead and use that to write R L naught transpose, and that's going to be R, and then the L naught transpose is going to give us an R inverse transpose, but it's a correlation matrix and it's symmetric, so we just get R inverse, and then we get A. I'm working on backwards here. We're going to get A transpose R inverse A inverse. And that simplifies down just a bit to A transpose R inverse A quantity inverse. Okay, so now we can express this a little bit, or go to our next complicated expression here. We're looking right now, we're interested in the ones highlighted in green. So this is going to be equal to L minus L naught A transpose R inverse A, all inverted, but we can multiply out this first expression and we get LA minus L naught A times the rest of it, R inverse A inverse, and we already know that this is going to be the identity matrix and that's going to be the identity matrix because that was the requirement on any matrix L that we chose, and so this whole thing evaluates to 0. Therefore the two green terms go away. Well, that's really nice. I'll put it up there. So now we have, let's summarize where we're at right now, that the trace of LR L transpose is equal to the trace of L naught R L naught transpose plus, without the two green terms, we just have one other term, the trace of, once again, myself more room, of L minus L naught R L minus L naught transpose. Well, R is positive semi-definite, and I guess it's got to be positive definite if we're going to be dealing with the inverses of R. So this is always, and the definition of positive semi-definite is that for any vector that you multiply, you will always end up with, on the left and right in the quadratic form, you always end up with something greater than or equal to 0. So R is positive definite. So this is always greater than 0. I should say greater than or equal to 0, because if L is equal to L naught, then the term evaluates to 0. Therefore, the trace of LR L transpose is always greater than or equal to the trace of L naught R L naught transpose for any L satisfying LA equals I. So we have now proven that that worked. Therefore, we can write definitively that our best linear unbiased estimator, blue, for the problem y equals a x naught plus b, where the expected value of E transpose is our correlation matrix and E is zero mean, is, and we write it this way, x hat blue is equal to A transpose R inverse A transpose R inverse